बिस्मिल्लाहिर्रहमानिर्रहीम रब्बी ज़िदनी इल्मा। ऐ मेरे रब मेरे इल्म में इजाफ़ा फरमा, आमीन। अस्सलाम वालेकुम class, I am your physics teacher Iram. We are studying chapter number 12, geometrical optics. Today our topics will be image formation by lenses, image location by lens equation, and sign conventions for lenses. After learning this topic, you will be able to draw ray diagrams for image formation in lenses, tell the nature of image formed by objects placed at different locations, and know about the sign conventions of lenses. Let's recap some important points. Lenses refract light to form images. As I have told you earlier that mirrors reflect light to form images, whereas lenses refract light to form images. So by drawing the ray diagrams, we will actually show the refraction. In concave lens, focus is virtual and focal length is taken as negative. As the concave lens diverges the light rays that are incident on it, so its focus is virtual and its focal length will be taken as negative. In convex lens, focus is real and focal length is taken as positive because convex lens is a converging lens. It actually converges all the light rays to a single point, that is its focal point, so its focal length will be taken as positive. Optical center is the midpoint of lens. It is taken on its vertical axis. Center of curvature and principal focus will be taken on both sides of the lenses, because now we have to show the refraction. So light rays can be incident from either side of the lens, from right or from left, and refraction, we have to show the refraction, so we have to take the principal focus on principal axis on both sides of the lenses. Let's start with the light ray rules for convex lens to draw the ray diagrams. There are some rules for drawing the ray diagrams. Let's study what are they. Number 1 is the ray parallel to principal axis passes through the focal point after refraction by the lens. These rules are actually 3 principal rays that we have to draw to show the refraction and image formation in the lenses. From that, the first ray should be parallel to principal axis and it passes through focal point after refraction by the lens. The second ray will pass through the optical center and it will pass straight through the lens and remains undeviated. The third ray will pass through the focal length, becomes parallel to the principal axis after refraction by the lens. You have to remember these rules to draw the ray diagrams. Let's see how the ray diagram will be drawn. For convex lens, here you can see a convex lens. I will give you some tips to start drawing these ray diagrams. First of all, you have to draw a straight horizontal line on your sheet. This is the principal axis. Then you have to draw the vertical axis of the lens. Here it is. You have to take same distance as from principal axis to upper part of the lens to principal axis to lower part of the lens. Means you have to take your pencil and scale and you have to measure 4 centimeter. Suppose you are taking 4 centimeter on one side and 4 centimeter on the other side of the lens, so that the principal focus should pass to the optical center of the lens. And here you can see F, the focal point drawn on both sides of the lenses. You have to take these distances equal. The distance from optical center to one side of the lens to up to focal point, and distance from optical center to this focal point, they must also be same. If you are taking 5 centimeter from C to F, then you have to draw again 5 centimeter from C to F on the other side. In next figures you will also see a distance 2F on both sides. What is meant by 2F? F is the focal length, so 2F will be double the focal length. It means if you are drawing C to F, if you are taking C to F as 5 centimeter, you will draw C to 2F as 10 centimeters. And here it should also be 10 centimeters. These points are important for drawing the ray diagrams. So keep them in your mind. Now we will see how that principal rays are drawn. First ray, you can see the green one is parallel to the principal axis. It is incident on the lens, and you can see we have drawn this ray up to the vertical axis, and then after it refraction is shown. It will bend according to the laws of refraction. So after diffraction through the lens, it will pass through focal point of the lens, and you have to extend it forward up to some this much point. So this is the first ray, this is the direction of incident ray, this is the direction of refracted ray. These arrowheads, you have to draw these arrowheads to show the incident and the refracted rays. So that was the first ray. Second ray, you can see it is red in color. It is passing from the optical center, and it goes straight, undeviated, in the straight path, undeviated. There is no refraction of this ray because it is passing from the optical center. This is the direction of incident ray, and this is the direction of refracted ray, which passes out from the lens, and you have to extend it up to a point where it meets the first ray. The third ray, that is passing from the focal point, that will touch the lens, and after refraction it becomes parallel to the principal axis. You can see from this figure that this is the incident ray which is passing from the focal point. That's why we have taken focal points on both sides of the lens. The light ray is passing from focal point. After refraction it bends in such a way that it becomes parallel to the principal axis. Here you can see that this principal axis and this ray are parallel to each other. So this is how we draw the ray diagrams for convex lens. Now we should discuss some cases. First we should see that how refraction occurs through lenses, through convex lens. Here you can see the image formation of a convex lens. The light rays are incident on one side of the lens, and they are converging on the other side of the lens. They are all converging to a single point. That means this is the real focus. The image will be real and inverted. That's why we will take the focal length of convex lenses as positive. Now, how images formed in the convex lenses? Let's see. This is a table which shows the size, orientation and nature of the images formed by convex lens. You can see that it all depends upon the location of objects in front of the lens at different locations. You can see that if the object is located behind 2F, the image will be real, inverted and smaller in size. Diminished means smaller in size. If it is placed at 2F distance in front of the lens, the image will be real, inverted and same in size. If the object is placed between 2F and F, the image will be real, inverted and enlarged. If it is placed at focal point of the lens, no image will be formed, so there will be nothing. If the object is located between F and C, C is the optical center for lenses. So if we place the object beyond, means between the focal length, inside the focal length of the lens, the image formed will be virtual, upright and enlarged than the object. So let's see by drawing the ray diagrams how it happens. Here is the first case when the object is placed beyond 2f. Let's see what will happen. Here you can see the object is placed beyond 2f. Don't get confused with this 2f1 and f1, f2 and 2f2, because these are just for our convenience, that we are taking number 1 for left of the lenses and number 2 for right of the lens. We have to just draw 3 principal rays according to the rules and we get the image formed, and from that image we can tell its nature, size and orientation. So here is the object placed between beyond 2f. So first ray, you have to draw the first ray that will be parallel to the principal axis. Here is the principal axis, so it is parallel. After refraction, it should pass from the focal point. It is passing from the focal point. You have to extend it. This is the direction of refracted ray. Second ray you have to draw passing from the optical center. Here it is. It passes undeviated. It has passed undeviated, and you have to extend it up to a point where it meets the first ray. Third ray is not drawn here. You can easily draw it according to the rule that it should pass from the principal focus, touch the lens. After refraction, it pass through the same point as the first 2 refracted light rays. So you get the image here. From this you can easily see it is smaller in size. It is present on right side of the lens. Object is here, image is on the opposite side, so it is real. From this orientation you can see that it is inverted and it is smaller in size to that of the object. Image will form, and where it is formed? It is formed between f and 2f. It will be real, inverted and diminished. That was the first case. Second case is if the object is placed at 2f. What will happen if the object is placed at 2f? Here is the case. Now object, we have taken the object at 2f. We are taking the object as an arrow. First ray, which is parallel to the principal axis, after refraction it is passing from the principal focus. It is passing like this. Second ray, you have to draw passing from the optical center undeviated. Don't get confused from this O, it is actually C. So you have to extend it up to this point where it meets the first refracted ray. Third one, you have to draw like this, passing from the principal focus, touching the lens. After refraction, it will be parallel to the principal axis and it will meet the first 2 refracted rays at a single point. Here the image is formed. Here you can see that the image will form at 2f. The object is present at 2f. Image is also present at 2f. It is real. Why? Because object is on one side, image is on second side. Other side, it is real. It is inverted. Real images are inverted and same in size. You can see the size of both of these object and images are same. So that is the second case. Let's discuss the third case. Third case is when object is placed between 2f and f. What will happen if we take the object more closer to the lens, that is between 2f and f? Here is the case. We are taking the object towards the lens at different locations. Now we have taken the object to a point which is present between 2f and f. So what will happen? You have to draw the first ray parallel to principal axis. After refraction, it is passing from the principal focus and you have to extend it. Second ray is passing through optical center and deviated. You have to extend it up to that first ray where they both meet. Third ray, you have to draw from this. You have to practice it yourself because here I think the lens is shorter. It will touch somewhere here and it will pass like this. So this is the case where what is the nature of image? You can see all these 3 principal rays are converging at a point where it is beyond 2f. After 2f, it is forming after 2f. It is very enlarged in size. It is real and inverted. So the image will form beyond 2f, real, inverted, and enlarged image is formed. Next case is when the object is placed at f. If we take the object to the focal point of the lens, what will happen? Here is the object. First of all, we have to draw the first ray. After diffraction, passing from the principal focus. Second light ray passing from the optical center, passed undeviated like this. So from these two, now as the object is placed at f, you cannot draw the third ray because we have to draw that third ray passing from the focal point. So here focal point is not available because object is lying over there. So you can see that both of these light rays are now parallel to each other. They will not meet on any side of the lens. So we can say that as the light rays are not converging, so no image will be formed here. Here is the last case. When object is placed between f and optical center, what will happen? Here we have taken the object to a point close to the lens like this. Here is the object, a light ray parallel to the principal axis after refraction passing from the principal focus. Another light ray passing from the optical center undeviated, passing undeviated. For drawing third ray, focal point is not available, so we have to just see where these two light rays will meet. As you know, see that these are not parallel, so we will extend them backwards. In this case, you can see these two light rays are converging on this point on same side of as that of the object. So what will happen? The image will formed at 2f on same side of the object. It will be virtual as the image and object are both present on same side. So this image will be virtual. It is erect because both of the image and object are of same size, but the image will be enlarged. Here you can see the mistake. This is the object, this is the image. Yes, so the image will be enlarged from the object size. It will be of the same size but large, of the same orientation, but the size will be enlarged as that of the object. In this case, the convex lens is behaving as a magnifying glass. Here you can see that it is behaving like a magnifying glass. How is it so? Because we have taken the object close to the convex lens. This is the case for magnifying glass, where the converging lens becomes a magnifying glass when an object is located inside the lens's focal length. The magnifying glass makes the image of the object, that is virtual, erect, and larger in size than the object. That were the cases for convex lenses. Now, how the light is refracted through a concave lens? We have to discuss refraction through concave lens. Image formation of concave lens. Image formation by concave lenses. Here you can see a concave lens. The light rays are incident on one side and they get diverged from the concave mirror. So they should be extended backwards to a point where they will meet. This is the virtual focus, and virtual and upright images will be formed, and then their sizes will be smaller whatever the location of the object will be. So we have to take the focal length of concave lens as negative because it's a virtual focus here. Light ray rules for concave lens for drawing the ray diagrams are same. Let's recall: the ray parallel to principal axis passes through focal point after refraction by the lens. Second ray will pass through the optical center undeviated, and the third ray will pass through the focal point, becomes parallel to principal axis after refraction by the lens. Let's see the diagram. Here you can see a concave lens. Again you have to follow the same rules. First of all, you have to draw this principal axis, then the vertical axis of the lens, optical center. Now take the first ray. It is parallel to the principal axis. After refraction, what should happen? It should pass from the principal axis, but as you can see, the light ray gets diverged. So how should it pass from the focal point? We have to extend it backwards. That's how it is passing from the focal point, as the focal point lies on the same side as that of the object. So here we can see the first principal ray drawn parallel to principal axis. After divergence, after refraction, it is passing from the focal point. Second light ray we have to draw from the optical center. It will pass from the optical center undeviated. Here it is. The second light ray follows the same path as that for the convex lens. Now the third one is somewhat confusing. You can see it is okay. What was the third rule for the third principal ray? It was that it will pass from the focal point, and after refraction it will become parallel to the principal axis. But how it will do so in through the concave lens? Just see that this is the light ray. Here it touches the lens, and after refraction it is passing it got parallel to the principal axis. So the third light ray is like this. We have to extend it backward so that it meets the first two light rays, and it will show the formation of image. Now how it is passing from the principal focus? You can see that as it is passing like this, after refraction it becomes parallel. If we extend this point, you can see that it is passing from the principal focus. So how you have to draw it? First of all, you have to take the scale. You have to take your scale and put it from in a manner that it will draw a straight line from object to this principal focus, so that from here you have to draw it as deviated from the refracted from the concave mirror, and it becomes parallel to the principal axis, and you have to extend it backwards for the formation of image, and you have to draw its original path to show that it should actually pass from the focal point, but it is refracted through the principal from the concave lens. So these were the light rays rules for concave lens. Now image formation in concave lenses. Here is a summary. Object position, whatever the object position is, you can see whether it is between lens and infinity, all of the points came in this range, f, 2f, between f and 2f, or between f and c. All these points lies between this range between lens and infinity. The image position will be within f. It will be on the same side as that of the object. The nature of image will be virtual, erect and diminished. If we take the object at infinity, the image formation will be on focal plane as same side of the object. Virtual, erect and diminished image will be formed. It means you can see that from concave lens, the nature of image will be virtual, erect and diminished, whatever the object location will be. Now, how can we locate an image using lens equation? The relation between object and image distance from the lens in terms of focal length of lens is called lens formula. This formula actually tells us that how far is the image formed from the lens, what is the focal of the length of the lens, what is the object distance from the lens. Means from in numericals we can find different different terms among the object distance, the image distance and the focal length of the lenses. Here is the formula. 1 by f equals to 1 by p plus 1 by q. You can see, you remember that f is the focal length, p is the object distance taken from object to the optical center of the lens, q is the image distance taken from image to the optical center of the lens. Here are the sign conventions for both of the lenses. As you know that this lens equation is used for both of the lenses, so some sign conventions must be used in order to see whether it is for convex lens or for concave lens. Here is the quantity object location. Object location, if the object is in front of the lens, it will be taken as positive. If object is at the back of the lens, it will be taken as negative. Image location, image is in back of the lens, it will be positive. Image in front of the lens as same side of the object, it will be taken as negative. Image height, if upright it is positive, if inverted it is negative. Means for concave lens it will be negative always. R1 and R2 radius of curvature is back of the lens and radius center of curvature is at in front of the lens. It is same as that case for the focal length. Focal length for converging lens it is positive, diverging lens it is negative. Another term used in this chapter is magnification. As I have told you, it is the ratio of image height to the object height. It is called magnification. Its formula is m is the symbol, image height divided by object height. It can be symbolically written as hi divided by h naught, means height of image or divided by height of object. Or it can also be taken as image distance divided by object distance, means it can be written as q by p. Both of these formulas are correct for magnification. A magnification not always means the enlargement of the image, it can also be taken for smaller images. Here you can see that the image is enlarged due to convex lens, so here the image is magnified, it is enlarged. If it becomes smaller, then the magnification is also there, but if the object is now magnified 1 by 3 times or 1 by 2 times or whatever it is, means it becomes lesser in size to that of the object. Now it's your homework, fill in the blanks. The focal length of dash lens is positive, you have to tell the name. The lens with long focal length will be dash, means you have to tell that whether a lens with long focal length will be thin or thick. A converging lens becomes dash when object is placed inside its focal length. A dash lens always forms smaller images. An object is 12 cm from a convex lens of focal length 8 cm. The position of image will be dash from the lens. You have to find out the position of image. Q is required F and P are given. Don't forget to uh, use the sign conventions for the lens mentioned here. You have to do the practice of these figures and examples on your sheets, and in case of any problem you can ask anything anytime. Thank you.